you. First of all, I'd like to say thank you very much for this opportunity for talking here about my research. I'm Pedro Dieguez. I'm now working as a postdoc at the International Center for Theory of Quantum Technologies in Gdańsk, Poland. And my talk is entitled Wave and Particle Realism in Quantum Delay Choice Experiments. Here's the summary of my presentation. I will start introducing the idea of Wheeler's original proposal of a delay choice experiment. And this is called in the literature nowadays as the classical version of delay choice, because in 2011 some authors proposed a quantum generalization for this experiment. This is called quantum delay choice experiment. And we're going to propose to use a measure of physical realism to quantify the definiteness of wave and particle in this kind of experiment. And then we're also going to propose a slightly different experimental arrangement to evaluate this physical wave and particle realism. And we call it this setup quantum controlled reality experiment. I will explain why we are giving this name. And to finish, I will present experimental proof of principle. It was implemented in using nuclear magnetic resonance techniques. So just to start very basically, it is we can talk about the wave and particle duality using a Mach-Zehnder interferometer. For example, here we start the experiment with a beam splitter, and we have two puffs and mirrors, and also a phase shifter which implements a relative phase between the two puffs. And the point here is that if we close the interferometer with another beam splitter, the output state of this experiment can be written like that, where theta is the relative phase between the puffs. And the point here is that if we look now for the probability distribution, for example in this detector, we can see that the probability is sensitive to the relative phase. Then we consider that this probability is linked with the wave-like behavior, so we assume that the system has behaved like a wave during the experiment. Otherwise, if we remove this second beam splitter, the output state of the interferometer can be written like that. And we know that if we have balanced beam splitters, the probability will not be sensitive to the relative phase. It will be 1/2 in this case. And this probability is related with a particle-like behavior. So by looking at the final probability, we make inferences about the wave and particle behavior in this experiment. We can say that the behavior is related to the physical context, so it is related to the experimental arrangement. And Wheeler asked a very interesting question, is what happens if we delay the choice to insert or not insert this final beam splitter here to be made after the system has entered into the interferometer. So after it traveled into the interferometer. And of course this experiment is very hard to implement, but it was realized in 2007, and we have here one of the authors of this paper. The classical apparatus, typically an interferometer, is defined only when the quantum system has entered it, and the result of the experiment is very interesting. No matter if you delay the choice, or no matter if you are delaying the choice to insert or not insert this final beam splitter, when the beam splitter is present, you look for the probabilities and you see a wave pattern, and when the beam splitter is not presented into the interferometer, you will see a particle behavior. So here are what is written in this paper. The complementarity, we can say that by looking at this experimental result, that the complementarity principle holds with this classical delay choice. And this is not the end of the history. As I said, in 2011, in this Physical Review Letters paper, these two authors proposed a quantum generalization of a delay choice experiment. So now, basically, the idea here is that instead of delaying the choice to be made after the system has entered into the interferometer and inserting or not inserting the final beam splitter, we are going to think that we can create a superposition. This, of course, this is, and it's schematically represented here, of a superposition of a beam splitter present and out at the same time in the experimental arrangement. Here I'm bringing experimental realization of this quantum delay choice experiment. It is a Physical Review A paper. It was made in 2012 using nuclear magnetic resonance techniques, and here is the final probability distribution of this experimental arrangement. To perform this idea of a superposition of a beam splitter, here the authors use quantum controlled operations. So we have an ancilla in such a way that if the ancilla here is written the state, if the ancilla is, for example, in the 0, we will apply operation analogous to a beam splitter, so I had a mark here in this example. And otherwise, if the ancilla is in the 1 state, we're going to apply just the identity in such a way that if we start the experiment with a coherent superposition, here parameterized by an angle alpha, we will apply both operations at the same time. So this is how this idea of a superposition of beam splitter is realized here in this context. The point here, this was the motivation of our work, and we asked it, by looking at this final probability, we can see that apparently we are measuring the both behaviors using the same experimental arrangement. Here is the particle behavior, and here we have a complete wave behavior. And but we asked ourselves if we can quantify the wave and the particle behavior using a measure of physical realism. But we asked ourselves if we can use this measure in the state when it is inside the interferometer and not using the state here at the output. And then, if we can do that, we asked ourselves how to connect this wave and particle behavior inside the interferometer with the final probability distribution, with the visibility of the interferometer. Okay, so this was our main motivation. And to quantify this wave and particle realism, we used this notion here of a measure. The original paper, it is Europhysics Letters, published in 2015 by Pedro and Angelo. And the idea here is to quantify the degree of definiteness for some observable. This measure here is contextual in the sense that it depends on the state and also on the observable that we are choosing. So basically the idea here is that, for example, taking a bipartite state O and an observable A, written here in terms of its projectors, if we assume a primitive notion that after some measurement of this observable, the measured property will be well defined independently if we have or not have access for the measurement result, we're going to assume that it is well defined in the sense that this CPTP map here, it is called non-selective measurement. It can define a way to define a state that has the realism defined for that observable. This is taken as the primitive notion of an A-reality state. And there are many properties to use this as a primitive notion of that. One of that is if we make another non-selective measurements, we don't change the state. And now by taking here the relative entropy between two states, define it like that, we can construct what the authors called Realism. This is called Realism because here it's not so clear, but here we have a minimization over all the possible states here. And we are taking the relative entropy between a state code that we want to evaluate the degree of realism and a state that has the realism defined for that observable. We can show that this minimization is given by this expression, whereas here stands for the von Neumann entropy, okay? And this is zero if and only if the state code can be written using this map like that. And also it is always positive and it is bounded by the logarithm of the dimension of the state. And there are many properties of this measure. One interesting property is that we can prove that this decomposition here holds. So the realism of some state, it always can be written as a sum of a local coherence term for this basis, and also a term which is related with the quantum correlations, because here D is the non-minimized version of the one-way quantum discord. And since it is bounded by the logarithm of the dimension, we can also write an expression to quantify the degree of realism and not its violation. Here is not to be consistent. It's logarithm of 2 here, not logarithm. Okay, so this was the measure that we used in our work. Here is the reference. It's experimental assessment of physical realism in a quantum controlled device. So, as I said, we analyzed the quantum delay choice experiment using this measure, and we saw that if we apply this measure on the state inside the interferometer, there is no way to connect it with the final probability distribution. So we proposed a new experimental arrangement, a slightly variation of that. I will explain in the sequence. And in this experimental arrangement, we made this connection with the final probability, specifically the visibility. And even in this new setup, we will show that both realism, wave, and particle cannot be simultaneously defined. I will show this result. So here are the two experiments that we made in this paper. We implemented again the quantum Wheeler's delay choice because there is a very important point here. We wanted to propose a new experiment, but with the same final probability distribution, so with the same visibility, and we succeed to do that by reversing the causal order between the first beam splitter and the quantum controlled interference. So here is the Wheeler's delay choice. And here is our quantum controlled reality experiment. So we start our experiment making the quantum controlled operation. Here are the use sequences used. As I said, it was implemented in nuclear magnetic resonance platform. We used two nuclear spins, the carbon-13 as the quantum ancilla to control here the interference, and the hydrogen as the system which entered into the interferometer, okay? Let me go. Here in red, we have the final probability distribution for the quantum Wheeler's delay choice. And here in blue, we have the final probability distribution for our proposal. We can see that it is exactly the same. The points here are this experimental results, and the curves are theoretical simulations using the experimental input. And here is the visibility of the experiment. They have, both of the setups have the same probability distribution, but the realism inside the interferometer is completely different. And here is the main result of the paper. In the green curve, we have, in the green and the purple, we have the results for the quantum delay choice. So using this measure of physical realism, we see that the wave realism is well defined all the time inside the interferometer, and the particle is completely undefined. And using our setup, we saw that this is a parametric plot, and we saw that the wave realism is it's connected with the final visibility in the way that if you increase the visibility, we increase the wave realism, and at the same time we decrease the particle realism. And just to finish, we take this property of the realism measure by two Lutwell-Mayotte observables. It is bounded, the sum of two realisms, and for pure qubit systems, we can show that this upper bound is related with the entanglement between the two systems, and we write this complementarity inequality here by showing that both of realism cannot be simultaneously defined in this experiment. And here are the conclusions. Just to summarize here all the results, and we are working using this measure in another foundational problems, and also trying to see if it can be written as a resource for quantum information and communication tasks. Thanks so much, and I'm finished.
I think we have time for two questions. Can I surround this?
Very strong. Very nice talk. How this notion of wave particle realism that you use basically to study complementarity here are related to previous notion like local realism, like Bell realism, macro realism,
Okay, nice question. In relation with the macro realism, we are trying to understand what is the relation. So it is, for us, it is an open problem. And with relation, in relation with Bell's non-locality, since the states here are pure, the two cube states are pure, all the entanglement here is also related with the non-locality in this sense.
I see. Thank you.
So I'll ask a question myself. So in, say, a dynamical collapse framework, a CSL theory or something like that, where the quantum state is something physically real, so it will reproduce the phenomena that you've been looking at, or plausibly so anyway. So in what sense then are you balancing realities? How would it look like if you were taking the quantum state to be something physically real?
I think that if we assume, for example, that collapse is real, when we make the final projection in the cylinder, we will just select one of these two results, or the wave or the particle.
The suggestion is that in such a theory, the quantum state is physically real throughout its evolution. So in what sense are you posing a problem, as it were, for reality?
Here, let me see.
So you're thinking there's either a particle reality, hidden variable, or there's a wave reality.
I do not see any problem in interpreting, for example, this measure as an ontology, as a real, saying real about the ontology of the state. For me, there's no problem.
Okay, on that happy note, let's thank the speaker again.